Welcome. I'm Rob Froney, and I'm here to talk about a two-input, two-output system. I want to give you an example of how to compute the gain parameters in this two-input, two-output system using the differential and the common mode. First of all, let's look at the differential and the common mode. We have two inputs to this system. We have VI plus and VI minus. Those are the inputs at the positive terminal and the negative terminal of the amplifier. And we can write those two inputs in terms of the common mode voltage right here, which is the average of those two, and the difference, that's the VI plus minus VI minus. The equations that describe those things are over here on the right. Now, here we have our matrix equation, which I explained in the last video, that describes the output voltage, both of them, V output differential and V output common mode, in terms of the input voltages, V input differential and V input common mode. Finding the parameters of this matrix in this special example is hopefully going to be helpful for you to understand in general how to do it. So, what are these parameters? First of all, the ADD up here is the gain parameter that gives you the differential output voltage given a common mode input given a differential input voltage with the common mode input voltage. That means that's set to 0. ADCM is the differential output voltage caused by a common mode input voltage with that means you need to set the differential input voltage to 0. So it's all common mode. The ACM, D is the common mode voltage that comes out when you have a differential input voltage, which means the input voltage is not common mode, or common mode part is 0. And the last parameter, ACM, CM, is the common mode output voltage caused by a common mode input voltage, where we've set the differential to 0 to make sure it was all common mode. Let's first of all compute the ADD. We'd really like that to be large, so I'm doing that in red. So first problem we have to solve is what are we going to put in for VI plus and VI minus? Well, you can get that from these equations here, or essentially you look at VI plus is VCM here, VICM plus half of the difference voltage. You can kind of see that from the diagram or the equations. Essentially, we just want to find out what VI plus needs to be and what VI minus needs to be. Now, I need to make sure that VICM is 0, and so to do that, I put VICM equals 0 in this. That means, this distance down here is pulled down to 0, so it goes kind of like this, right around, it's pivoting around 0. And so that tells you I want VI plus equal to half VID and VI minus equal to minus a half VID. So I put that as an input right here and as the input down here as well. And because we have negative feedback in this circuit with RA and RB, we can use the summing point constraint, which says the voltage at the inverting and non-inverting terminals are the same. So I put those simplifications in here. At this point, you can see there's going to be a current going down through RC because we have a VID on the top and a minus VID on the bottom, so there's VID across it, and if we take VID divided by RC, I get the current. That's this equation right here. Now, what we really want is the output differential voltage divided by the input differential voltage. So now we have to compute the output differential voltage, which is Vout plus minus Vout minus. So what we need to do is, if we notice this circuit here, if I take the voltage right here minus the voltage right here, that is just this current that's going through here times the sum of the resistors. And the current going through RA is the same as going through RC because there is no current coming out of the op-amp inverting input, and similarly for the bottom here. So writing that down, I have Vout D is the difference in the output voltages, Vout plus minus Vout minus, and that's I times the sum of the resistors. So replacing I with this VID over RC, we end up with this equation right here, from which we can see that AD comma D is this sum of the resistors over RC. So we'd like that to be big, so all we have to do is make RA and RB big, and we will get this sum is always, this gain is always going to be greater than 1. Okay, let's look at one of the other elements here. This time what we're going to do is we're going to compute ACM comma D. So that's the common mode output voltage with still a differential input voltage. Because the voltage is still differential on the input, I still have plus VID over 2 and minus VID over 2 here. I still have I coming down through RC, and the only difference in this one between this one and last one is I need to get the output common mode voltage. So the best way to do that is to take V out and solve for V out plus, and then solve for V out minus, and then take those two things and average them, because that's the common mode output voltage. So here's V out plus. Remember that we had I going through this thing right here, and the voltage on this terminal right here at this position is VID over 2. So if I take VID over 2 plus I times RA, I get V out plus, and that's just what I wrote right here. If you substitute in the I we have up here, you get this. Similarly, for V out minus, I take the voltage at this terminal, which is minus VID over 2, and then I have drop by RB times I, so I subtract RBI, and I get this voltage right here. Now, finding the V out common mode, I average the two V out plus and V out minus right here, and this is what that is, and it boils down to this expression right here. So the RA minus RB over 2RC is the ACM comma D. And I'd really like that to be 0. So I'm going to pick RA equal to RB. Now that makes this circuit right here into a very nice symmetrical circuit, which is what we would expect if we want to remove the common mode output. Let's look at another one of these matrix elements. This time I want to do this one right here, AD comma CM. And so now we're going to have a different voltage on the input, because this is due to the common mode input voltage. So I have to figure out how to make VI plus and VI minus set up so it's a common mode situation. So if you notice from the equations up here, VI plus is a half VID plus a VI common mode. Now I want VID to be 0, so I'm just going to have VI plus is VI common mode, and likewise VI minus will be V common mode, because VID is 0 there. So in this case I have V common mode here and V common mode here. Using the summing point constraints, that's V common mode at this node and V common mode at that node, which means there's 0 current going through RC. If 0 current is going through RC, then I've got essentially 0 difference in the output voltage V out plus minus V out minus, because I have essentially I've got you know, a 0 times RA plus RC plus RB, and so I've got 0 output voltage here, which means the gain is going to be 0. So AD comma CM is 0. That's something I really like. Okay, so now let's look at the last matrix element. That would be ACM comma CM. That's this guy right here. And we're going to have an input common mode voltage again, so we put the same voltage on the input. But here I have to compute the output common mode voltage, and like we did with the other output common mode voltage, I'm going to find V out plus, and I'm going to find V out minus, and I'm going to average them. So if we notice, this I is again 0, because we're putting in a common mode voltage. And if I is 0, then the voltage VICM right here on the inverting terminal of the op-amp is going to be the same as V out plus, because there's 0 current going through RA, and that means the IR drop is 0, and so V out plus is equal to VI common mode. Similarly for V out minus. And so when you take the average of V out common mode with itself, you get V out common mode. So if you notice, the output common mode is equal to the input common mode voltage, which means the common mode to common mode gain is 1. That's not as good as I'd like. I wish it was 0, but at least it's the minimum number I would get for A differential. So here's our final matrix with those values that we got, and we can look at, here's the output voltage, here's the A matrix, and here's the input voltage. And the A matrix right here, if I do that, is going to be it's good. The ADD, if I make RA and RB the same, is going to be it's going to turn out to be 1 plus 2 RA over RC. This term in the matrix was 0, this term was 0, and this term is 1. And so that's the A matrix right there. And so I've got V out vector here equals this A matrix times the V in vector, and these are the common mode and differential. This is the V in vector, right, V out vector right here, and this is the V in vector right there. So I hope this was helpful.